Let's review. Newton's first law of motion states that an object in motion will stay in motion, and an object at rest will stay at rest unless an external force acts upon the object. But how do we describe such a force? A force is a bit of an oomph that can make an object go faster, slower, or in a different direction. When multiple forces act on an object, we can take their sum to get a net force. The magnitude, or quantitative value, of a net force is simply the sum of the magnitudes of all the contributing forces. The direction of a net force is the sum of the directions of all the contributing forces. Newton's second law states that the net force acting on an object is equal to its mass times its acceleration. Acceleration is a change in the velocity of an object over its time and is often written in units of meters per second squared. Mass is the amount of matter an object contains and is often given in units of kilograms. So if you're ever feeling particularly massive, just think to yourself that you matter a bit more in that moment. Since force is equal to mass times acceleration, it is given in units of kilograms meters per second squared. And that's kind of a mouthful, so we usually just say newtons. Newtons are the unit of force in the SI metric system. Let's say you walk into a grocery store and start pushing a stationary cart up to walking speed, which is about 1.5 meters per second. The push you give the cart is a force. The acceleration of the cart can be calculated from the change in its velocity and the amount of time that has passed by. Since it is going from 0 meters per second to 1.5 meters per second, the change in velocity is 1.5 meters per second. If it takes you 3 seconds to get the cart up to walking speed, the acceleration is 1.5 meters per second divided by 3 seconds, or 1/2 meters per second squared. If the mass of the cart is 20 kilograms, then the force of your push is 20 kilograms times 1/2 meters per second squared, or 10 newtons. Now, if we ignore friction, the cart will keep rolling at a speed of 1.5 meters per second down an aisle. But wait! You've been up all night studying physics and really need to stop to pick up an energy drink on the shelf. You suddenly stop in the aisle and pull on the cart's handle so that it comes to a halt. The cart goes from a velocity of 1.5 meters per second back down to 0 meters per second in 3 seconds, so the force you are applying by pulling on the cart is once again 10 newtons. Once you put the energy drink in the cart, you will need to push the cart to get it moving again. Will this push require more or less force than the first time you pushed the cart? If the acceleration is the same as before, the cart will require more force than before because the cart, with the addition of the energy drink, is slightly more massive than before. Since force is equal to mass times acceleration, either an increase in mass or an increase in acceleration will force to increase. Let's play with some numbers, shall we? If you accelerate a 1,000 kilogram car from 20 meters per second to 30 meters per second in 2.5 seconds while merging onto the freeway, how much force is applied? The acceleration would be the difference in velocity, 10 meters per second divided by 2.5 seconds, or 4 meters per second squared. Multiply that by the mass, 1,000 kilograms, to get a force of 4,000 newtons. Now, what if it takes 200 newtons to decelerate a bike at a rate of 20% gravity? How massive is the bike? Well, gravity is 9.8 meters per second squared, so 20% of that would be 1.96 meters per second squared. To get the mass of the bike, you must divide its acceleration, or in this case, deceleration, from the force. 200 newtons divided by 1.96 meters per second squared is about 102 kilograms, so the mass of the bike is about 102 kilograms.